Process control is the use of control techniques to regulate process variables and ensure that a process remains stable and consistently produces a good quality product. In this video, I'll introduce you to the basics of process control. By the end of the video, you will know what a process is and what are the two main types of process, the difference between open-loop and closed-loop control, the components that make up a control loop, and the most common process control strategies used in industry. Process is the transformation of raw materials into end products through operations like mixing, heating, cooling, filtering, and storing. These raw materials are typically in liquid, gas, or slurry form. Process industries include chemical manufacturing, oil and gas, food and beverage, pharmaceutical production, water treatment, and power generation. There are two main types of process: continuous and batch. In a continuous process, material flows constantly, and each piece of equipment runs in a single dedicated state. Continuous processes rarely shut down because there is generally a massive cost associated with starting the process and getting it to a steady state. The goal of a continuous process is to keep the output consistent regardless of how long the process runs. Cement kilns and oil refining are examples of continuous processes. In a batch process, the process has defined start and end points and produces discrete quantities of material called batches. Each batch can be traced back to the specific input materials used to produce it. Brewing beer is an example of a batch process. In this process, a specific amount of raw materials are loaded into the process, and after passing through each stage of the process, a batch of beer is produced. The batch of beer can be traced back to the raw materials that were used to produce it if required. There are two ways to control a process: open-loop control and closed-loop control. In open-loop control, an action is taken regardless of the current process conditions. A simple example is setting an air conditioning unit to switch on at 10 a.m. and switch off at 7 p.m. every day. The action always happens, regardless of the current temperature of the room. Open-loop control is simple and inexpensive to implement, but it is often inefficient. In closed-loop control, the current condition is measured, compared to a target value called a set point, and corrected if there is a deviation. Closed-loop control is the basis of process automation. Closed-loop control can be manual or automatic. In manual closed-loop control, a person monitors the process variable and adjusts the output manually. They may do this by opening or closing a valve by hand. In automatic control, a controller makes those adjustments without human intervention. Process control is often implemented on PLCs. To learn more about how to program Allen Bradley PLCs for process control, check out our Learn Logix course series. Realpars members get access to these courses and all of our other great courses on industrial automation. Learn more at realpars.com/business or by using the link in the description below this video. A closed-loop control system is made up of three main elements: a measurement device or sensor, a controller, and an actuator. Sensors, also known as primary devices, measure the process variable. Sensors may be equipped with a transmitter. Transmitters convert the raw sensor readings into scaled engineering units that the controller can use. Common sensors used in process control include temperature sensors, pressure sensors, and flow meters. The process value is sent to a controller, which compares the process value to the set point. Based on the difference between the two, the controller calculates an output to drive the process value back toward the set point. The output signal is sent to an actuator, which physically controls the process. Examples of actuators include heaters, pumps, and control valves. Now that you know how a closed-loop control works, let's look at the control strategies used to manage process loops. The most common control strategy is a PID loop, or proportional integral derivative. PID is an algorithm that controls a process using three configurable dimensions: proportional, integral, and derivative. Each dimension is tuned to match the behavior of the specific process being controlled. To learn more about PID control, PID tuning, and implementing PID loops, check out our PID Controller Basics course using the link in the description below. Two-state control is used for simple devices that have only two positions, on or off. A basic on-off valve is a good example. When the process variable falls below a threshold, the valve opens. When it rises above another threshold, the valve closes. In selective control, two or more control loops feed into a selection instruction, and the output that wins drives the actuator. This strategy is often used to protect equipment, so it is often the lowest value that wins. For example, in a pipe system, one PID loop may be used on a flow meter and another on a pressure sensor. The flow meter loop may demand more flow to meet the set point, but if the pressure is rising too high, the pressure PID wins. This protects the equipment even if the flow set point is not fully met. In split-range control, a single measurement signal drives two actuators that complement each other across the output range. A heat-cool loop is a common example. Depending on the process value, either a heater or a cooler is pulsed to control the set point. This approach allows the use of simpler digital devices instead of more expensive analog ones. Feed-forward control compensates for known disturbances before they have a chance to affect the process variable. This is useful when feedback from a measuring device is slow, as it prevents large swings in the process before the controller has time to react. Feed-forward requires mathematical modeling of the process and can be difficult to implement. Ratio control maintains a fixed ratio between two input streams. One stream flows in uncontrolled, and the second is calculated and adjusted to stay in proportion with the first. Acid dilution is a practical example. If a process requires 1 part acid to be diluted with 3 parts water, the water may flow freely, and the acid flow is continuously calculated and adjusted to maintain that ratio. In cascade control, two loops are linked together. The secondary loop reacts faster to disturbances and adjusts the actuator before the slower primary variable is affected. A common example is a reactor with a temperature jacket. The primary loop controls the product temperature inside the reactor. The secondary loop controls the jacket temperature, adjusting the steam valve in response to jacket temperature changes before those changes have time to affect the product temperature. In this video, I introduced you to the fundamentals of process control. Specifically, you learned what process control is, what types of processes exist, the difference between open-loop and closed-loop control, the structure of a control loop, and common control strategies used in process control. And if you're a plant manager looking to train your maintenance team, visit realpars.com/business. Fill out the form and book a call with our team.